Bonjour à toutes et à tous. Dear colleagues, thank you for attending the Research Days of DigiCosme. I am Elie Awwad, and together with Catherine Lepère, we are coordinating this academic year the Optical Communications Task Force. Today I will be talking about some of the current works and prospects of OCOMEX. Optical Communication Task Force, or OCOMEX, started in 2017. Initially, the focus was on optical fiber communication systems, for which several bottlenecks remained unresolved, such as a further capacity increase and the limitation of energy consumption. The capacity increase can be achieved by mitigating or embracing nonlinear noise, for instance, as well as by opening new spectral windows or adding new dimensions, such as the spatial dimension, through the use of multimode or multi-core fibers, for instance. This new multiplexing dimension requires MIMO processing to separate the spatial channels at the destination, so a lot of effort was done in this direction. A new research topic emerged in the following years related to machine learning algorithms that are leveraged to enhance the performance over both physical and network layers. After that, a new axis appeared to be very interesting, with the revival of optical wireless communications, such as visible light communications and free-space optical communications. I will focus today on two hot topics that I will be presenting and illustrating with some use cases. The first hot topic is in the context of optical fiber communications. We chose to study machine learning solutions for the physical and network layers. And our goal is harnessing the potential of artificial intelligence to enhance the design of optical fiber transmissions and to allow them to operate in the best possible conditions. Three use cases are presented here to illustrate these. First, in dynamic optical networks, adding or dropping channels leads to power excursions that need to be dynamically controlled. Power excursion prediction and precompensation using reinforcement learning was considered to limit this impairment in the work of Maria José in a thesis supervised by Catherine Lepère. A second use case deals with the monitoring of the losses along a link, or the power loss profile. With Alex May and Philippe Sibla, we were investigating how to use the mitigation of nonlinear effects to spot power anomalies in the link. The enhanced monitoring can help us reducing allocated power margins and reducing system outage by maintaining an up-to-date version of the channel state information. And because the mitigation of nonlinear effects are power dependent, this is exploited to estimate the anomalies in the link. A third use case is to use machine learning to mitigate nonlinear noise in long-haul optical transmission systems. Given that nonlinear effects accumulate in a complex manner, depending on the modulation formats and baud rate of the WDM channels, as well as on the system architecture, artificial intelligence-based solutions seem to be a suitable tool for nonlinear noise mitigation. The second hot topic relates to optical wireless communications. These technologies have witnessed a revival recently among researchers in both academia and industry. The motivation behind this interest includes relatively simple deployment, unlicensed bandwidth, and higher data rates than other technologies. Again, I will illustrate with three examples our efforts. First of all, in the domain of ground-to-satellite and satellite-to-ground communications, I mentioned the PhD work of Laurie Paillet with the ONERA and Yves Jaouen. In this work, an architecture of a coherent receiver with adaptive optics was studied in order to increase the rates with coherent technology. Indeed, coherent technology allows the use of in-phase and quadrature modulation formats, and hence the use of higher order modulations to increase the rates. A modeling of the atmospheric disturbances was also considered. A second action in the frame of indoor visible light communications is our contribution through Catherine Lepers to the Light Communication Alliance. The aim of VLC, for visible light communication, is to establish indoor positioning and enable the combination of illumination and communication functionalities. Last but not least, I mention a work on studying the capacity bounds of free space optics intensity channels by Michel Viger, which considered FSO intensity channels subject to an average intensity and peak intensity constraints to compute lower and upper capacity bounds. New prospects include the design and implementation of practical schemes to demonstrate the ability of FSO technologies to achieve high data rates. As you have seen, a diversity of topics are covered by our research teams, ranging from physics to information theory. If you're willing to contribute, please feel free to contact me or Catherine so we can connect you to the relevant scientist and researcher. I benefit from these research days to announce an upcoming seminar that we are preparing in machine learning for optical fiber transmission systems that will be held in March 2021. Stay tuned for more information and please contact us if you are interested in contributing. Thank you for your attention and have a good day.